Greetings. Hey everybody. I should be live now. Let me know in chat if that is the case. I'm gonna... Hey Lord Pyjo. Good to see ya. Let me get my face up here. There I am. That's not very clear. Might be some gunk on my camera. That's a tiny bit better. Learning a new language. Yeah, I'm gonna explain that in a second here. But I've got the flickers again, like usual. Okay, maybe that'll work better. Who knows? And then I'll also get, actually, yeah, I'll do that. Keycaster. Alright, get these up there. You can see what I'm typing, and then I'll blow up my font a little bigger. Cool. Alright, that should suffice. Let me go ping the Discord, and I'll be right back with you. Live streams. All right, I'll wait like 1 minute here and then I'll get started. All right. I will jump into it. So these streams are good. Basically just going to be like me learning, like the learning time that I'd be doing anyway, but decided to stream them just to be doing a little more on my channel. And so I'm going to start off with OCaml. So I already sort of partway learned some of OCaml a while ago. And so part of this is going to be like relearning. So I might go sort of fast through some of it. But I'm gonna start from the beginning again and might just go sort of quick. So we'll see how this goes. All right, so I think if we go to like learn, and then, okay, so there's a few ways to learn this. There's like this one, like textbook with like videos that go along with it, which is like kind of the really thorough. Oh yeah, this is the one, I think, right? Yeah. This is like the thorough, slower way, but since I already am sort of familiar with some of the concepts, I'm going to kind of do the quicker way. So there's like a get started thing, which has a bunch of articles here, including a tour of OCaml, which kind of like runs you through the basic concepts of the language, and then language, which then goes more in depth. So I wonder if I want to, if I need to go through this, if I'm going to go through, like, what does this do? Expressions, definitions. Functions. Yeah, that should all be covered over here, right? These kind of go in order. All right, well, let's start with the language tour and then I'll jump in. And I already have it installed, so I don't have to go through this installing, I don't think. Yeah, 5.3, or at least that's the open. Yeah. Did I? Looks like I installed that with Homebrew, which I generally don't really like, but oh well. Okay, so I'll start with this. It's for OCaml. I'll make this a little bigger for you guys. You should be able to see that pretty good. I already installed OCaml, and then we're gonna use the Utah to use the top level. So this is like a REPL for OCaml, so it's gonna use this to do some things. Expressions, definitions. Start with this. Okay, everything has a value, everything has a type. I'm just wondering if this is worth, or I should just go to here. What are the sections in here? Like how far does this get? Variant types, records with errors, exceptions, mutable state, modules in the standard library. Yeah, okay, let's just go to language because that'll all be covered, right? Maps. Like where are records going to be covered? Oh, that's searching packages. Oh, probably that's basic data types. Tuples, functions, unit. Yeah, here we go. Yeah, variant record aliases. Okay, so that's all in here. Perfect. Okay, so we'll just run through these then. I think this would be better. Okay. Values and functions. Functions are treated as values. You can use functions as arguments to functions and return them from functions. Yada yada. First class functions. Use Utah. Sure. What is a value? An expression-oriented programming language. That means programs are expressions. Actually, almost everything is an expression. Statements don't specify actions to be taken on data. All computations are made through expression evaluation. Yeah, okay, because it's like functional. Computing expressions produces values. Below you'll find a few examples of expressions, their type, and the resulting values. Some include computation, some do not. So it's saying you can do like 2 times 21. And then in the, okay, this is one thing I'll have to learn that I never really figured out. It's like what the double semicolon really means. Actually, I think I did figure that out at one point. I just forget what it meant. Hey, Mart. Okay, I will proceed. Int of float, I guess, is a function that takes floats and makes ints. Int of float. Function that goes from float to int. Cool. I can say int of float and then pass it a value like this. 59, which is about pi times 2.0. Whoops, I need that. Array constant that has type float. Wait, what? Oh, I used the wrong. This is, okay, this is the operator for floats, and that's the one for ints. That's right. Forgot about that. Cool. Also, another thing, I think after I've kind of gone through some of this stuff, I'm going to try to make Thorsten balls, writing an interpreter in Go, but like in OCaml. So making the monkey programming language. Just as like a learning project for OCaml. You can make your own function like this. I'm assuming I can bind that to my own thing. Like that. And now I can like square 2 and I get 4. Cool. Print end line is a function that returns a unit. So if I print end line lorem ipsum, then it prints lorem ipsum, sure enough. Cool. Global definitions. Every value can be named. This is the purpose of let something equal something statement. The name is on the left, the expression is on the right. If the expression can be evaluated, it is. Otherwise, the expression is turned into a value as is. That's the case of a function definition. That's what happens when writing a definition. Yeah, I already tried this. Okay. So you like bind with let. It looks just like lots of other languages. Local definitions. Bind a name inside of an expression. Okay, yeah, this is cool. So like, I can say let d equal t or 2 times 3 in, and then this d is bound to this within the scope of whatever comes next, right? Which is generally another expression. Or I guess always another expression. So this should be what? 2 times 3 is 6 times 7, which is who knows what? 42. I am a math major, by the way. But now, okay, yeah, and then the example is like, okay, now what is d? D is undefined, right? Because d was only defined within this scope after the in. So that's fun. Computation transfer will always take place before d times 7. Yeah, so it always computes from the outside and then uses those values inside. Local definitions can be chained one after another or nested, one inside another. Here's an example of chaining. Oh, cool. So you can say d equal 2 times 3, so we get 6, in let e equal d times 7, in d times e, 252. That's neat. And now they're both, neither of them are defined outside of here. Here's how scoping works. Yeah, I think we get that. Whoa. Wait, this is like mind bending. E is bound to 6 inside E times 5. Yes. D is bound to 30. Wait, so we're getting 210, right? So E times 5. So E is 6 times 5 is 30. And that gets bound to D. Oh, that's interesting. Okay. And then you multiply that by 7, you get 210. Interesting. Okay. Pattern matching is a programming language construct that generalizes case analysis. It makes sub-expression inspection possible and applies to values of any type. Following sections, we explore pattern matching inside let bindings, which is a special case. In the next chapter on basic data types and pattern matching, which is this one, examine pattern matching in general using match with. The chapter on error handling explores how destructuring values aids. Like, where's this error handling thing you speak of? That's in his guides. So there's also these guides. That's cool. And some of these we'll probably just be referring back to as we make a real world project. And I'm not too concerned about like figuring everything out right off the bat. Okay, let me put my phone on silent so it doesn't buzz again. All right, pattern matching and definitions. When pattern matching only has one case, it can be used in name definitions and in let something equals and fun something expressions. In that case, less or more than one name may be defined. This applies to tuples, records, and custom single variant types. I'm not sure. I need an example. A common case is tuples. It allows the creation of two names with a single let. Oh, gotcha. Oh, that's interesting. So list.split takes like an array of tuples, so like a list of some A and some B. These are like generics, the tick A and tick B. I think they're called alpha beta. So like a list of alpha beta. This is a tuple type because it's a product type. Creates a list of alpha and a list of beta. Interesting. So I can, this is basically just destructuring, right? So let xy equal list dot split, and then we're passing it a list. Oops. Etc. Right? That's what we get. So 1, 3, 5, 2, 4, 6. We get the odds and we get the evens, which is fun. And this would work with any types as long as they're the same, right? So now we get an int list and a string list, right? So we got 1, 3, 5 and 1, 2, 3. Except for I forgot to change the. This makes more sense, doesn't it? Well, there we go. 1, 2, 3 numeric, and then 1, 2, 3 English. Cool. Pattern matching on records. We can pattern match on records. We haven't learned about records yet, but they're basically what you'd expect. They're kind of like TypeScript objects, I guess. Although there's a formatting issue right here. This should have a space in front of it to fit with all these. So we can define that. So type name equals first string last string. So now you have a type name. First Robin, last Milner. And because of the Milner here, not because of that, but because it uses a Hindley-Milner type system, it infers that this is name, even though I never specified that this was name, which is obviously much better than what TypeScript can do. So that's really neat. I wonder what it would do though if I added something else. Unbound record field. Okay, so this isn't a defined type, so I can't do that. That's super interesting. Okay, and you can destructure here as well too. That's cool. So I can say like let first equal given name, last equals family name equal Robin. I need one more semicolon. And so it kind of pulls out. Yeah, Rust can do similar things to this. This is neat. Pattern matching in function parameters. Single case pattern matching can also be used for parameter declaration. Here's an example with tuples. Right, so we got to let get country, which takes a tuple, which has the country and first, last, and that is of type string name country. All right, and you also wouldn't have to add that, and then it'd become generic, right? Because country could be anything here. But for the sake of sticking with the example, we'll say this has to be a string. Just an example with a name record. I guess it's basically just showing that. Oh, I get. Okay, so it's just saying that instead of like having this be like A and then having to like index in here to like A dot 0, or I don't know how they do it in OCaml. You can destructure it within the arguments, which is cool. Let introduce first last. I am first last. Yeah, okay, that's cool. So you can do it right in there. Let introduce first, last. I am, and I guess this is the string concatenation operator, first, last. First, okay. So now if we have like introduce, I think we have Robin still kicking around. I'm Robin Milner. Cool. Using the discard pattern for a parameter declaration is also possible. Oh, okay. So you can just ignore parameters. I don't know when this would be useful. Get meaning. And since we never made anything that would restrict what the type of this would be, it just can be anything, so generic to K. Because it always infers like the least specific type possible. So if I get the meaning of anything, it'll always be 42. Even if it's like Robin, the meaning of Robin, it's also 42. Okay. Pattern matching on unit. Special case of combined definition and pattern matching involves the unit type. So the unit type is written like this. Explained in this, which I skipped. The unit type is a single value. Yeah, we know how to work with units. Units also in they're written like this in Rust too. Okay. The pattern does not contain any identifier. In order for compiled files to only value an expression for its side effects, you must write them after that. Okay, that makes sense. Pattern matching on user-defined types. This also works with user-defined types, yada yada. Nested pattern matching on user-defined types. Okay, yeah. Yep. The following example demonstrates two methods, yada yada. Discarding values using pattern matching. Okay, so you can discard this, is just like Rust, right? You can stick a thing in there. Scopes and environments. Without oversimplifying, an OCaml program is a sequence of expressions or global let definitions. Execution evaluates each item from top to bottom. At any time during evaluation, the environment is the ordered sequence of available definitions. The environment is also known as context in other languages. Here, the name 20 is added to the top level environment. So if I say val, or not val. Wait, what's val versus let? Oh, it's because I'm reading it wrong. This is the definition. This is what the thing spits back at you. Let 20 is 20. The scope of 20 is global. This name is available anywhere after the definition. Here, the global environment is unchanged. Okay. Equal 10 in 2 times 10. Because there's no 10, but it is a 20. That's interesting. So when we do let something in, this just becomes, this is an expression, right? Whereas this is a global let, right? And that is adding something to the global environment. It has a few statements. The global let modifies the global environment by adding a name value binding. Yeah, so global lets are expressions, are statements, and most other things are expressions. Top level expressions are also statements because they are equivalent to let something equal that. Oh, gotcha. Inner shadowing. Once you create a name, define it, and bind it to a value, it does not change. That said, a name can be defined again to create a new binding. Okay, so this is like shadowing. right? That's cool. So I can say like let I equal 21, and then I can say let I equal 7. And then I can, and I is now 7, right? But I could also do something here. Right, but I here is still 7, but I'm using it for something different in here. Cool. Same level shadowing. Oh, that's what I did over this and then this, right? Functions as values. In OCaml, functions are values. Key concept of functional programming. In this context, it is also possible to say that OCaml has first class functions. Yep. Applying functions. When several expressions are written side by side, the leftmost one should be a function. All the others are arguments. In OCaml, no parentheses are needed to express passing an argument to a function. Parentheses serve a single purpose, associating expressions to create slow expressions. Okay, so we're saying like max 21 times 2 int of string 7 13. So max takes 2 of something and returns 1 of them. I'm curious about this int of string though, because shouldn't that be able to error? Like what happens if I do this exception? Okay, so I guess it just throws. I'd rather return like a result type, but when creating simple expressions using begin end is also possible. It's the same as using brackets, or these are parentheses, not brackets. As such, the above could also be rewritten and get the same result. Okay. So begin end is the same as like using parens, right? So this could be end, begin, and begin. It just seems a little bit verbose. Oh, cool. So you can have, this is like something that'll come later, but these are labeled arguments, which is nice. I'm a fan. String.starts with prefix is state, stateless. It's true. But if I did stateless, that would be false. Have label parameters. Labels are useful when a function has several parameters of the same type. Naming arguments allows to guess their purpose. Above prefix state indicates state is passed as labeled argument prefix. Labeled and optional parameters are detailed in the labeled arguments tutorial. Cool. There are 2 alternative ways to apply functions. The application operator, which is at. So instead of like squirt of 9, I can do squirt and then I apply that. Okay, interesting. Not sure when I would want that, but there's probably a case. Applies an argument on the right to a function on the left. It is useful when chaining several calls as it avoids writing parentheses. Oh, interesting. So instead of writing int of float, square root of float of int of string 81, right? Which is 9. I can get rid of all these parens. And do that. Which is nice. Then there's the pipe operator, which everybody kind of knows about, which takes the same thing but does it backwards. So you take like 81 and then pipe that into int of string, and then pipe the result of that to float of int, pipe the result of that into the square root, pipe the result of that into int of float. Still get 9. Anonymous functions. Functions do not have to be bound to a name unless they are recursive. Take these examples. Yeah, okay, so these are just like free-floating functions. Oh, this is pattern matching. We haven't seen this yet. Like, what does colon mean? I don't know what this means. Function values are not bound to names. Sorry, function values not bound to names are called anonymous functions. Yep. Oh, this is like the, what do you call it? Like the cons operator that like takes the head and the tail. Interesting. Yeah, so you can pass these as arguments. This is like map. Yeah. So list.map takes a function and a list. A function that maps A to B, and then a list of A, and then returns a list of B. And so if I have a list dot map, right, the function would go in here, and then like some list, like 1, 2, 3, 4. Then I can just pass the function in here, like the square function. X goes to x squared, and then you get those all squared, 1, 4, 9, 16. Cool. Defining global functions. You can globally bind a function to a name using a global definition. Yeah, okay, so you can square, I already made square, so let f equal fun x times x. This expression, which happens to be a function, is turned into a value, but here's another way to do the same thing. So this is like the syntactic sugar for this above. You can just say let gx, right? This is the function name right here, and then function parameter. And you can add more parameters. Gx equal x times x. So I can say like g3, and I get 9. Defining local functions, they can be defined locally. Same thing, so you can say like let square x equal x times x, and then in, and then this becomes an expression. You can do 49 times 49. Who knows what that is? 2,401. But it's not defined out here because it's local. Cool. Closures. This illustrates a closure using same level shadowing. Wait, what is happening? Wait, so okay, you say let j equal 2 times 3, so j is 6. Sorry. And then let kx equal x times j. Oh, I see what's happening here. And then you do k7, right? So it takes whatever you pass it and multiplies it by j, which is 6. So 7 times 6 is 42. And then you say let j equal 7. So we're redefining j, right? And then we get k7. And you think it might switch it to 49, right? Because now we have 7 times 7. But no, because it captures this value as a closure, right? So you still get 42. Pretty standard closure stuff. Recursive functions. In order to perform iterated computations, a function may call itself. Such a function is called recursive, which is kind of like a core concept in functional programming. And so this is like a good example, like Fibonacci, right? So you have to use rec here if it's recursive. Fibo, so Fibonacci, and you take a number, you say, okay, if n is less than or equal to 1, then just return it, else n minus 1, right, plus Fibo n minus 2. Boom. Second, like Fibo 0 is 0, Fibo 1 is 1, Fibo 2 is also 1, and then Fibo 3 is 2, 4 should be 3, 5 should be 5, right? 6 should be 8, and then we get like what, 13, 21, and so forth. Okay, perfect, it's working. This is a very inefficient way, I guess. I don't know why it's inefficient. I wonder what the more efficient way is. By the way, it's using this list.init. What is that? It's a standard library function that allows you to create a list by applying a given function to a sequence of integers. Oh, cool. And fun.id is the identity function. Oh, that's actually really handy. So like list.init 10 okay, wait. It takes an int and a function that takes those ints and turns them into that and returns a list of those things. Okay, so like list init 20 and then fun.id. It's the identity function, I guess. So you just get 0 through 19. That's nice. All right, here's some other. Second version uses the first two Fibonacci numbers as initial values. There's nothing to be computed when returning from a recursive call, so this enables the compiler to perform an optimization called tail call elimination. I never quite understood tail call elimination. What does this link go to? Oh, perfect, a Wikipedia article. All right, I will look into that to be checked out. Doink. All right, and then functions with multiple parameters. Defining functions with multiple parameters. Oh, this is where it gets really interesting. So like sweet cat xy equals x something y. Why is that sweet cat? Okay, kitty cat. That makes sense. Anonymous functions. Okay, look like that, and there's a reason they look like that. It's because of partial application, right? Yeah. Okay. So basically, any function, like if I have like mult, if I make something mult x y, or let mult x y equals x times y, right? So that mult is a function that goes from int to int to int, right? And the reason it's not just like int comma int to int is because it's actually a function that returns a function that returns that, right? So I can partially apply mult. If I just mult 3, I get a function, right? That takes one int and returns another int, right? So this is a function that will multiply whatever I pass to it by 3, right? I'm having a hard time explaining this, but this basically explains it right here, I'm sure. So I can say like let foo or mult by 3 equals mult 3, right? Mult by 3, which I guess I called multi by 3. If I do 4 now, then I get 12, right? So basically mult 3, 4, which is equivalent, right? Is the same as saying, okay, mult 3, which gives us a function that multiplies by 3 by 4. Which is really interesting, and which is why the signature of mult is int, as opposed to something like in some other language would look more like this, because it's not that. This is a little bit mind-boggling for me at first, but I kind of remember it from last time I went through this. Partial application is so sick. Yes, 100% guy 98. It's super awesome. All right, since multiple, oh yeah, okay, I just talked about that. Types of functions of multiple parameters. Well, this is what I just talked about. Okay, yeah. Tuples as function parameters. If you want to pass a tuple, then you can pass tuples. And this basically gives it more behavior that's more like normal functions from other languages. Like you pass both these in at the same time as a tuple, as opposed to like one and then the other as with partial application. So this looks more like a normal function call, but it's really just one parameter that's a tuple instead of 2 parameters. Oh, and then there's currying and uncurrying, which I do not remember what they are, but I remember thinking they're really cool. 2 kinds of multiple parameter functions. Oh yeah, it's basically where you convert the tuple thing into the partial application thing, I think. Functions returning a function such as sweet cat and sour cat. Functions taking a tuple as a parameter such as spicy cat. Okay, both kinds of functions provide a way to pass several pieces of data while being functions with a single parameter. From this perspective, it makes sense to say all functions have a single argument. This goes even further. It is always possible to translate back and forth between functions that look like sweet cat or sour cat. I don't even know what these examples were, but I get the point. These translations have names. Currying goes from spicy cat form into sour cat form. Which one's which? Spicy cat is, okay, like taking a tuple into a partial application, which is like this. Sour cat, where's sour cat? Here we go. Yeah, sour cat. Okay, so that's currying. So currying like breaks it apart into multiple things. Uncurrying lumps it together. So this is curried, this is uncurried. Yeah, that's pretty awesome. Is there like a... Here, this is shown using string as an example, but it applies to any... Oh yeah, it's named after Haskell curry. Applies to any group of 3 types. You can change the curried form into the uncurried form when refactoring or the other way around. However, it is also possible to implement one from the other to have both forms available, which is neat. So I'm going to try to make an example. So I'll say like, okay, if I let mult curried mult equal, sorry, x, y, right? This is curried, int. And if I say let uncurried mult, this would be like x, y, right? So it takes a tuple and then returns x times y. So instead of int to int to int, it takes like an int by int, which is like a tuple, a product type, and it returns an int. So curried mult would be used like 3.2. Also allows for partial application, right? So I can get that, which is cool. And then uncurried would have to be used like 3.2. Curried functions are default because they allow partial application. There's no parentheses or commas, and there's no pattern matching over tuple, which is nice. All right, functions with side effects. Explain side effects. We need to define what domain and codomain are. Let's look at this, yada yada. I think we understand this. Effects lie outside of function types, right? As well as wider. Functions are often said to be either pure or impure. The former does not have side effects, the latter does, yep. All right. It's like print and line obviously has side effects, so it's not pure. There's no meaningful data to return, so it returns just the unit value. Okay, gotcha. What makes functions different from other values? Functions are like other values except for their restrictions. Function values cannot be displayed in interactive sessions. The placeholder fun is displayed instead. This is because there's nothing meaningful to print. Equality between functions can't be tested. Okay, that makes sense. There are 2 main reasons explaining this. There's no algorithm that takes 2 functions and determines if they return the same output when provide the same input. This seems like there's got to be some math proof for this. That's like really famous that I don't know about. Assuming it was possible, such an algorithm would declare that implementations of quicksort and bubble sort are equal, which is not true because they have the same output, but okay. Gotcha. Conclusion. Awesome. Oh, there's exercises. All right, we'll hold off on those. Okay, basic data types and pattern matching. Let's jump to this one. By the way, probably gonna go till about 9 o'clock, maybe a little before. Because then I gotta start my real job. So cool. We already did that. Oh, actually, we skipped that one, but that's okay. And we did values and functions. Introduction. All right, there's a lot of types. So there's integers, floats, booleans, and characters. So integers is what we've been dealing with a bunch. Platform dependent assigned integers. This is good to know. Usually has 31 bits and 32 and 63 and 64. Okay, so int is kind of like a use size, or no, it'd be like an I size, right? Yeah. So int is equivalent to I size in Rust, or an int, right? So int is equivalent to I size in Rust. So right, OCaml equals I size in Rust equals int in Swift, right? So like on this machine, it's a 64-bit unsigned. The standard library also provides these, which is cool. That's nice. Platform independent operations on 32 and 64-bit signed integers. Not detailed. Okay. So if I want to have other sizes, then I can reach out for those. Cool. Hey, Robin. Good to see you. Usually int. I just read that. Sorry. There's no dedicated types for unsigned integers and OCaml bitwise operations on int. Treat the signed bit the same as other bits. Okay. Binary operators are standard symbols. Gotcha. Floats and type conversions. Float numbers have type float. Okay, so there's another thing called float, which I believe if you just add a decimal point, that it infers it as float. Yeah, cool. I guess I don't need the 0. Can you just do this? Or 2 dot? Yeah, cool. And then there's different operators, right? Because like this is for ints, and this is for floats, and then same I think with everything, like all those. If you add the dot afterwards, it becomes for floats, which is kind of what's showing here. You make like pi, and then tau is like 2 times pi, right? And you try to do tau is 2 integer times pi, right? This is an integer. This is a float. You cannot do that. You'd have to convert this. This is Boolean, so true is a bool. Nice, nice, nice. If then else is a conditional expression. Okay, so I can do like 3 times if foo equals bar then 5. I really like how they only have a single equals. That's super nice. Else 5 plus 2. We get 21 because foo does not equal bar, so we go to the else, so we get 5 plus 2, which is 7 times 3 is 21. Okay. Char or car or care, however you want to say it. Values of type char correspond to the 250. Okay, this is like ASCII characters, right? I'm assuming. What's equivalent to ASCII? You surround it with single quotes. That's confusing that I chose that. Okay, like that, which is different from this, which is a string. Okay. Oh, and then there's for Unicode, there's a uchar module, which is cool. String and byte sequences. Strings are immutable, meaning it's impossible to change a character's value inside a string. Great. Strings are finite and fixed size sequences of char values. The string concatenation operator symbol is the caret. Indexed access to string characters is possible using the following syntax. Buenos dias, dot 4. Okay, dot bracket. So we got buenos dias, dot bracket 4. We get O, right? So this would be 0, 1, 2, 3, 4. Okay, so 0 indexed. Interesting. Operations on string values are provided by that and that. Okay. Byte sequences. You can convert that to bytes. What are bytes? So I can say string dot 2 bytes. Hello. And we get some bytes. So bytes is a type. It's a byte sequence. The string's byte sequences are finite and fixed size. Each individual byte is represented by a char value. Like arrays, byte sequences are mutable. Meaning they can't be extended or shortened, but each component byte may be outdated. Okay, so it's like a string, but mutable? Essentially, a byte sequence type bytes is a mutable string that can't be printed. Interesting. There's no way to write bytes literally, so they must be produced by a function. Operations on bytes values are provided by standard lib and the bytes modules. Oops, I accidentally clicked on that. Only the function bytes.get allows direct access to the characters. Ooh, okay, so let me hello bytes. String got 2 bytes. hello. So if I say bytes.get, what is this thing? Takes bytes. Okay, so if I bytes.get hello bytes, and then 2 should give me an L. Actually, 1 should give me an E, right? I got an E. Cool. So let's take an index into this. By the way, folks, did I mention, I said this on Discord, but after I get somewhat comfortable with OCaml, I want to check out this OCaml thing that Jane Street's been working on. Seems pretty compelling. Where was I? Okay, and then we have arrays and lists. Arrays are finite and fixed sized sequences of values of the same type. Here are a couple of examples. So to make these array literals, use these like bracket pipe, whereas lists are just the brackets. Interesting. So I can make an array 1, 2, 3, and then pipe bracket. So that's an int array. They may contain values of any type. Here arrays are int array, char array, and string array. Those ones there. But any type of data can be used in an array. Usually array is said to be a polymorphic type, which means like generic in other languages, I think. Strictly speaking, it is a type operator, but it accepts a type as argument here. To form another type, those inferred here. This is the empty array. Okay. Take A, alpha as a type parameter that will be replaced by any other type, or by another type, sorry. Like string and bytes, arrays support direct access, but the syntax is not the same. Okay, so instead of dot bracket, use dot parens. Not sure why. Arrays are mutable, meaning they can't be extended or shortened, but each element may be updated. Oh, interesting. So I could say letters equal v x, it's hard to type, y z. And I could say letters 2, and then use this like back arrow for mutation, which is actually kind of cool. I like that. Makes it F. So now letters is VXF. So it's mutable. Literals, lists are very much like arrays, same types, but they don't have the pipes and they become lists. Like arrays, lists are finite sequences of values of the same types. They are polymorphic too. However, lists are extensible, immutable, and don't support direct access to all the values they contain. Okay, so they're extensible. Okay. So arrays can't be extended or shrunk, but you can change individual elements. However, lists, you can add items to them, but you can't change individual items, and they don't support direct access to all the values they contain. Lists play a central role in functional programming, so they have a dedicated tutorial. Gotcha. I think they're linked. They are linked lists in OCaml. So, list.append function concatenates two lists. It can be used as an operator with a symbol at. Okay, so that's append. So if I have 1, 2, 3. I would append it with 4, 5, 6. I can do so, and I get 1, 2, 3, 4, 5, 6. Very nice. There are symbols of special importance with respect to lists. Oh, for some reason the empty list is called nil. That's interesting. The list constructor operator, written : and pronounced cons, is used to add a value at the head of a list. Yeah, okay, so 3 like cons empty becomes just 3. If I do 3 cons 4 becomes 3 comma 4. So you just add elements to it. Oh, and you can chain these, which is cool. Like that, you go 1, 2. Very nice. Pattern matching provides basic means to access stored data inside a list. Oh, cool. Hey, Zaya or Zia. Good to see ya. Match 1, 2, 3 with, and then here's some options, right? X, U, X, or if it's empty, I guess this is like a exception, right? We get 1. Just like returns the first element. Above expression is the value that is matched over each expression between that is a pattern. Yeah, we know about those. It's pretty simple. Options and results. These are just like or options is just like Rust at least, right? None is an option. Sum 32 is also an option, an int option. Here's an example of pattern matching on an option value. Cool. Operations on options are provided by the option module. Options are discussed in the error handling guide. Cool. Results. All right, okay, so I can say okay 32 int a. So like this is like the value type, this is the error type. So like the value type is inferred as that. If I have error, sorry, then the value type hasn't been inferred, but it knows that the error type is string. Cool, so that's also very similar to Rust. Tuples, we already know about tuples. I can do like 3 or 2 comma 2. It's inferred as the type int asterisk string. This just shows it's a product type, I think. Well, first is a built-in. And so second. How about third? I don't even know how that would be. All right, so I guess you can take out first and second are built in. Interesting. Standard library, both are defined using pattern matching. Here's how a function extracts the third element of a product of 4 types. Gotcha. Functions. The type of functions from type M to N is written M to N. Yeah, we already know about this. Okay. Functions may terminate without returning the expected type value by throwing an exception of type EXN. Hey there. Good to see ya. R. Brahmaditya. Not sure how to say that. No way to know a function may raise an exception without inspecting its code. Okay, so exceptions aren't typed. That's good to know. They're discussed in error handling. Functions may have several parameters. Yep, we know this. Okay, unit. We know about unit as well. User define. Okay, this is where it gets interesting. So there's variants, records, aliases. Variants are also called tagged unions because that's what they are. Enumerated data. Okay. Yeah. So these are Lovely's gonna look very much like. Actually, Lovely's literally gonna look exactly like this syntactically. So I can say like, yeah, type character class equals barbarian or bard or cleric or druid or fighter. I'll just do this. So we have that type, and then I type rectitude. Type rectitude is evil, or why are neutral? Oh, because neutral, they have it for both. So it's like rectitude neutral. R neutral, neutral, or good. And I can say type firmness equals chaotic or neutral or lawful. Okay. Yeah, you can use these for any kind of thing. Unordering is defined on values following the definition order. Oh, okay, that's interesting. So Druid is less than Ranger. Rectitude to French is interesting. If you use this function keyword, then it immediately matches on them. It's just, okay, yeah. Because this is syntactic sugar. So if you have let rectitude to French, and then you have R being like your thing, and then you say like match R with, and then dot dot dot, this is equivalent to if you just leave that off and say function, and then start matching on them. Evil, mavois, I have no idea how to speak French. Are neutral, neuter, and then good, bon. Very nice. Now if I say rectitude to French, evil, gives me that. Perfect. Constructors with data. It's possible to wrap data in constructors. Okay, so these are like associated values on enums basically. You say hash of string, tag of string, branch of string. Cool. And then you can match on those. That's cool. Very nice. And this is what I explained before. Like the function dot 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 is used instead of match that with that. Wrapping product types with parentheses turns them into a single parameter. Yes, we know this. Recursive variants. Yes, okay, so you can make these recursive. Polymorphic data types. Yeah. Okay, so this is cool. So I can make like a type a described, for example, which is like a string. I guess I can't. Wait, what did I do wrong here? Oh, because it'd be this. Just needs to be a type. There we go. Okay, so now I can say like I can make something that is that's that, and that is the same type. I would have to write that it's that, I guess, for it to register as that, but it is that. Cool. Product types also behave as variant types. For instance, pairs can be seen as inhabitants of this type. That is interesting. Int bool pair would be written as that, and pair of that would be written as that. From the developer's perspective, everything happens as if such a type were declared for every possible product shape. This is what allows pattern matching on products. Okay. User defined polymorphic types. Yeah, we just did that. Okay. And then there's records, which are like objects in like TypeScript or something. All right, aliases, type aliases. Okay, so you can just, that's like what I did here or here. Oh, cool. You can alias function parameters too, which is nice. Okay. I'll do that. Conclusion. Awesome. Let's do, probably don't have time for this whole one, but I'll start this one and then that'll be it for this morning, but be back at it tomorrow. As in other OCaml.org documentation, the code examples will either be something you can test or, okay. Okay, what I want here is my own how do I make my own your first OCaml program? Here we go. Let's try this so I can actually write some of this stuff out in a real project. I'm going to mkdir OCaml. And then I'll go hop into OCaml. Cool. And then let me shrink this a smidge. Okay. And then I will. I already installed it, and we already did that. You already have an open switch. All right. Exec. Perfect. So that made hello. Hello has all these things in it for me. Oops. Try running Dune build. Build. What if I open that now? Oh, cool, and that works. Very nice. And then my build, everything goes in here, right? So that's probably the get ignored. Actually, let me just add it. This isn't even a get thing though. Okay, so now that's ignored. Test. Okay. Very nice. And I think, where does my default, where is my this, is that it? Where do or I guess when I build a project, I guess it'll probably explain this tutorial on it. I guess you can do tune exec hello. So like runs it. Okay, cool. I don't know why the opam exec. That make sure it's like does it on your right. Seems to be like the same thing. I'm sure there's a difference. We'll find out. All right. Do I have to recompile before? Okay, so that's like kind of like cargo run, I guess. Very nice. Watch mode. Watch mode exists. Okay, so that's always watching. That's nice. Dune is by Jane Street, right? Oh no, it's by OCaml. I think Jane Street is the one that like was originally making Dune. There's no requirement for a main function. Okay, it just compiled. It just runs it from the top to the bottom. All right, so we got this running. Now we can, in theory, hop back over to here. Although it wasn't here. Loops and recursion, right? For, okay, so we got these things for variable. This was a rather limited form of the familiar for loop. Limited, I think, because they want you to use recursion when you can. We can even do down to. That's kind of cool. So you can like backtrack. All right. Doesn't support the concept of breaking out of a for loop early. Has no break, continue, or last statements. Okay. You could throw an exception and catch it outside, but this would run, and this would run fast, but often looks clumsy. Okay. So there's hacks around this, but generally they want you to use recursion, I think. Okay. And then there's while. So generally don't use these. Because there's better ways. Okay, interesting. Let's try this. Why is nothing working here? Oh, there we go. Printf, okay. And then we do list.iter. Recently tried OCaml in web dev context, and it was hard to find job scheduler example for periodic jobs. Oh, interesting. Sorry, that's wrong. My list isn't a thing. Okay, let me get on my list. Yeah, that's what I want. I think you can also open printf, and then I don't need like that. Cool. Can I run it? Very nice. Okay, so list.iter. Just runs this function on each element of my list here, which is cool. And then we made our function here. We could have inlined it, but this is good. And it knows that this takes an int because it knows that this needs to be an int to be that, I guess, which is interesting. Cool. Decided it was not ready for web dev. Yeah, I haven't tried it. Well, I haven't really tried it for anything, but I'm curious what it's like for web dev. List.iter is what you should think about using first every time your cerebellum suggests you use a for loop. Okay, so instead try to use list.iter. If you want to transform each element separately in the list, for example, doubling each element in the list, and use list.map. Yep. We could do that here. List.map. Oh, cool. And they're using, because, oops. This might look like, that doubles. Let me get 2, 4, 6, 8, 10. This might look like magic here. This is just, sorry, would that shrink down? This is just using, I don't know why the syntax highlighting isn't working, but this is just using the multiplication operator as a function, and then partially applying 2 here, so it becomes like the double function, and then applying that to my list, the elements of my list, which is pretty crazy. All right, let's do a little more here, and then I'll stop for today. All right, and then you can filter list.mem, short for member, so check if you have something. Cool. For all and exist are the same as for all and exist operators and predicate logic. Okay. It's also fold left and fold right, which are like a reduce in some languages, or it's also called fold, I think, in Rust. All right, we'll stop there. Next, we'll do looping over strings. So we'll be here next time. Thanks all for joining. And yeah, I'll be doing this again tomorrow morning, I believe, and I'll let you guys know in the Discord and stuff. So until then.